So here is a nice application of determinants. This is called Cramer's rule. We address the situation of solving a system of equations, ax equals b. Now, the Cramer's rule, very importantly, only applies if this coefficient matrix is square and invertible. And so it only applies in this restricted case. But that being the case, here's the weird little rule. Suppose our matrix A is made up of column vectors, and I want to give these column vectors names. I'm going to call them A1 through AN. And the solution vector here, x, I'm going to look at its individual coordinates. We'll call those x1 through xn, like so. Okay. And I'm going to make this weird little definition now. This is very strange. What I'm going to do is take the matrix A, and I'm going to find the ith column. Now, the ith column has a vector in it we've already agreed to call A sub I. And what I'm going to do is trample that by placing in that location instead this B vector. Everything else will stay the same, so all of these columns don't change. Right? I'm just going to replace what had been the ith column instead with the B vector, namely the right-hand side from the system. What an odd little definition. And here's why we're interested in that, though. Turns out that if you're interested in solving for the ith coordinate of the solution, then this little formula will do it. It's the determinant of this AI matrix divided by the determinant of the original matrix A. Very surprising. So weird that this seemingly unnatural process of just trampling one of the column vectors and replacing it with the constants on the right-hand side would have anything to do with the right answer. But it works. So we're going to see why this works. I'm going to take another quick moment to emphasize how surprising this is. By making the observation that at a glance it seems that we've replaced certain category of numbers with completely different kinds of numbers. So in particular, these numbers are coefficients in the system, and what we're replacing them with are not coefficients in the system. They're the constants on the right-hand side of the equation. It seems like they're being put in the wrong place, somewhere that they just shouldn't be. They have no business being there. And that's one of the things that makes this result so surprising. Okay. All right, so let's see why this works. And the first important thing to realize is that what I just said is very misleading. It is not true that B has no business being related to the columns of A. In fact, matrix multiplication says exactly that the vector B is a linear combination of the columns of A. Right? So all of a sudden, not so unnatural seeming. The idea that these numbers, that the column vector of B has nothing to do with the columns of A, false. Right? It is very closely connected to the columns of A. Okay. All right, so now let's remember this AI matrix that we're interested in. Where did it come from? Well, you take the A matrix. The A matrix, by and large, doesn't change, except for in the ith column, we put the B vector. All right, so here we go. The A matrix stays largely the same, except for the fact that in the ith column, we put the B vector. And let's not forget, we just made this realization that the B vector that I'm putting in the ith column is this linear combination of the columns of A. So all I've got here then is this is an expanded representation of this matrix AI. Okay. So in our computation of the determinant of AI, which is going to end up being fruitful, we find ourselves taking the determinant of a matrix that has a linear combination in one of the columns. Well, now this just begs for us to apply the multilinearity. Right? Multilinearity addresses exactly this question of when you're looking at a determinant of a matrix where one of the columns, or rows, but in this case columns, is a linear combination. So what I'm going to do then is exactly that. I'm going to take this determinant and I'm going to apply multilinearity in the ith column. Now remember, with multilinearity, all of the other columns don't change at all. Right? So all that stuff doesn't change. None of that stuff's allowed to change. Right? All that we do when we're applying multilinearity is we take the linear combination that's on the inside in that ith column and we expand that out to the outside. So in particular, these coefficients x1 through xn, the vectors that we're taking linear combinations of, a1 through an, those vectors stay in and the coefficients come out. Okay, so all I've done here in going from this equation, in going from this expression, this determinant here, down to this expression, is apply multilinearity and take the linear combination on the inside and move that, transform that into a corresponding linear combination on the outside. Okay. All right. So now let's look at this expression. I claim that there's something wonderful about this determinant. It leaps off the page at you. We have in the ith column, we have a1. But we also have a1 in the first column. So there are two identical columns, and therefore this determinant is 0. That term goes away. Fantastic. Likewise, there's something interesting about this determinant. You see we have an in the ith position. Oh, but of course we also have an in the nth position, and therefore we have two identical columns, and therefore that determinant is 0, and that whole term goes away. Okay, and this applies to most of the other terms. Most of the other terms disappear because in most of the other terms, what I have in the ith position is a column vector that's also in one of the other positions. And so there are two identical columns. Okay. The only term that does not correspondingly disappear is the term where what I have in the ith column is not in any of the other columns, because what I have in the ith column is a I, which is only in the ith column. There is no other column that is AI. So that's the one term that doesn't go away. So altogether then, the determinant of AI is xi times the determinant of A, and therefore I can solve for xi, and it's that divided by that. Okay, so it's a wonderful little result, just because it's so surprising. I will point out that this is not a very efficient way to solve an actual system of numbers, because, well, gosh, look how many determinants you'd have to compute. Going back to the result here, in order to compute just one coordinate of the solution, I would need to compute two determinants, right? Now, of course, the one on the bottom, I only have to compute it one time, but I still, grand total, would have to compute n plus 1 determinants, which best case would be n plus 1 row reductions. So instead, why don't I just row reduce, right? So from a computational standpoint with actual numbers, this is not an efficient choice. Okay, but let me remind you, that is not always the situation that we face. We are not always trying to just solve equations involving actual numbers. Sometimes you have a system of equations and everything in sight is a variable. So let's see an example. might have coefficients A11, A12, A21, A22, and your unknowns x1, x2, all right, and then you have let's see here, I'll use red, B1, B2. Maybe these are all parameters representing variables under your control in an experiment. And you might want to know, okay, look, I'm interested, most importantly, I'm interested in understanding the behavior of x1, but I want to know, how does x1 change when I tweak that number a little bit, right? If I start to change that number around, what's the derivative? How fast does x1 change as I change a12? Right? Well, in order to answer that question, you need a formula for x1 as a function of a12, and this gives it to you. Right? So, in a situation like that, Cramer's rule can be extremely convenient, extremely useful.